Furthermore, the measurement range is only plus or minus 1/1000th of an inch. In addition, cap gauges are sensitive to contaminants on the target and probe surfaces, stray capacitance, and temperature fluctuations. Finally, it should be noted that although probing is non-contacting, a very small force is exerted on the target surface due to the associated electric field. To make a displacement measurement with this cap gauge, first ensure that the probe is secured to the appropriate connector on the rear of the console, that is, probe A with connector A. Power up the console and allow time for electronic stabilization. After warm-up, select the channel matching the probe being used. Select range A, the range with the largest measurement spread. Select the mode desired, which in this case will be A. Select the display mode to static. Position the 10-turn electronic fine adjust knob in the middle of its range. Using a sturdy mounting fixture, carefully position the probe next to the target surface such that the display needle indicates 0. Remember, the target surface should be smooth and the target must be a conductor. If possible, wear gloves to minimize body heating of the equipment. Avoid contacting the delicate surface of the probe tip. Secure the probe cable, taking care to avoid placing it near sources of electrical noise. Allow time for thermal equilibration of the test equipment and the surrounding environment. If another range is desired, switch to that range, and if necessary, use the electronic fine adjust knob to re-zero the display. The separation of the target surface and probe tip may now be varied with the variation being displayed by the cap gauge meter or the analog voltage output. Another high-resolution, small displacement measuring instrument is the electronic indicator gauge. This lever-type indicator gauge converts displacements of the stylus into voltages via a shaded pole inductor circuit. This particular instrument offers resolution down to plus or minus 1 microinch. Measurement linearity is 0.1%. While this instrument's measurement range of plus or minus 0.01 inches is an extremely attractive feature, its low frequency response of 300 Hz precludes its use in dynamic measurements. Although this is a contacting measurement device, the gauging force for this stylus is less than 0.2 ounces, a force which may be acceptable for many applications. Other measurements might be undermined by the deformations resulting from these small contact forces. While these forces are very small, the contact areas are even smaller. Therefore, the contact pressure becomes sufficient to produce measurable distortion of both the specimen and the stylus. These distortions obscure the true dimension, especially if the contact force varies over the course of the measurement. A direction switch allows gauging in either stylus direction. Notice that the stylus displacement is actually rotation rather than translation. To compensate for cosine errors due to this angular motion, the tip of the stylus has an involute geometry. The gauge console offers 5 measurement ranges, as well as a plus or minus 10 volt analog signal. The available ranges are plus or minus 0.01 inches, plus or minus 0.002 inches, plus or minus 0.001 inches, plus or minus 0.0002 inches, and plus or minus 0.0001 inches. The voltage to displacement conversion factor for the analog signal depends on the range selected. A choice of metric or English units is also offered. Verify that the stylus unit's cable has been connected to the rear of the console. Power up the console and allow time for electronic stabilization. After warm-up, select the range with the largest measurement spread. Position the electronic fine adjust knob in the middle of its range, that is, at 0, 0. Using a sturdy mounting fixture, carefully bring the stylus into contact with the measurement surface so that the display needle remains on scale. Using the mechanical course adjust knob, position the stylus such that the display needle indicates 0. Again, if possible, wear gloves to minimize body heating of the equipment. Secure the probe cable, taking care to avoid placing it near sources of electrical noise. Allow time for thermal equilibration of test equipment and surrounding environment. If another range is desired, switch to that range, and if necessary, use the electronic fine adjust knob to re-zero the display. The position of the measurement surface relative to the stylus may now be varied, with the variation being displayed by the indicator gauge meter or the analog voltage output. The last distance measuring instrument to be discussed in this lab is the linear laser interferometer system. These systems have nearly half microinch resolution, as well as measurement ranges exceeding 100 feet. While not as high as those of capacitance gauges, typical frequency responses of 10 kilohertz are quite adequate for dynamic measurement. In our system here, a helium neon laser produces a beam containing two frequencies of coherent monochromatic light via a process known as Zeeman splitting. These two frequencies have different polarizations and may therefore be separated and recombined through the use of optical components. The separation of the two frequencies occurs at the interferometer's polarizing beam splitter. The reference frequency component, F1, is directed through a fixed path by the stationary retroreflector, while the measurement frequency component, F2, is subjected to the path length variations created by the movement of the measurement retroreflector. A Doppler shift or frequency difference results from the motion of the retroreflector relative to the interferometer. The reference and measurement components are recombined, and this frequency difference is detected as an interference fringe by a photodetector in the measurement receiver. This frequency difference is converted to a velocity corresponding to the motion of the retroreflector relative to the interferometer. Finally, the velocity term is integrated to obtain a distance value. In addition to velocity and distance measurement, laser interferometry also allows the measurement of angular displacement, flatness, straightness, squareness, and parallelism. While laser interferometry does have many advantages, like the other instruments, it also has its disadvantages. Perhaps the biggest shortcoming of laser interferometers is their sensitivity to atmospheric changes, temperature, humidity, barometric pressure, and even carbon dioxide content. Variations in these environmental conditions cause changes in the refractive index of the air through which the beam travels. Changes in the refractive index result in uncompensated changes in the wavelength of the light. Variations in the standard with which you measure obviously undermines the validity of the measurement. Environmental errors can be quantified by determining the refractive index changes and calculating the resultant wavelength changes. The magnitudes of the refractive index changes are given by the Edlin equation. Shown here is another way of expressing these effects. For every 1 degree Celsius temperature change, expect 1 microinch of measurement error. For each 0.1 inch of mercury change in the barometric pressure, expect another microinch of measurement error. For every 30% change in humidity, figure on yet another microinch of measurement error. The effects of environmental error can be reduced by manually changing the environmental parameters on the measurement unit or through the use of automatic velocity of light or refractive index compensators. To make a distance measurement with the laser interferometer, the optical components should be aligned as shown. Always ensure that the beam exiting the laser enters the optics in accordance with the directional arrows on the optics. To simplify the setup, the reference retroreflector may be mounted directly to the interferometer. However, if environmental errors exist, dead path error or uncompensated environmental error will be introduced. Dead path error occurs when the environmental errors exist for a system in which the reference path and the initial measurement path are not equal. When refractive index compensators are used, they assume initially equal path lengths to which the correction is to be applied. Therefore, compensators do not correct for dead path error. The measurement retroreflector and interferometer should be aligned such that the laser's measurement beam is collinear with the axis of displacement. Remember that the interferometer will be stationary and the measurement retroreflector will be movable. If the measurement beam is not aligned with the displacement axis, cosine error is introduced. That is, the measured distance is really the actual distance times the cosine of the misalignment angle. The laser head should be securely mounted to a vibration-free base or stand along the measurement axis. Turn the turret ring on the laser head to other. The laser beam will exit the top port and will return through the bottom port. With the interconnecting cable, connect the laser head to the laser source port on the rear of the measurement display. Power up the system and wait for the completion of the warm-up routine. During this warm-up period, the display will read laser cold. When the system is ready, the display will read laser up if the beam is being received by the detector, or path error if the beam is not being detected. The laser on indicator on the front of the laser head should now be lighted. Unless the laser beam aperture control is closed, the red laser beam should be visible. While skin irritation from this low power laser is unlikely, eye damage is a real danger. Never look into the laser or stare at the beam's reflection. In between measurements, the aperture control may be closed to avoid exposure to the laser beam. The gun sight method will be used to precisely align the optics. Select the aperture control's smaller opening for the laser beam's exit port. Rotate the target over the return port. Using the translation and rotation adjustments on the tripod, position the laser head so that the interferometer assembly's returning beam falls on the target over the return port. With the retroreflector as near to the interferometer as possible, adjust the position of the retroreflector until its return beam is also centered on the return port target. With the optics at their minimum separation, attach an alignment target to the interferometer such that the beam passes through the hole in the target. Attach another target to the retroreflector so that the beam falls on the target's crosshairs. Gradually move the retroreflector away from the interferometer until the beam has nearly moved off the retroreflector's target. Rotate the laser head horizontally and vertically to move the beam back toward the target's crosshairs. During this process, the beam will probably become partially blocked by the interferometer target. Now horizontally and vertically translate the laser head until the beam again passes through the hole in the interferometer's target. Continue this process until the far end of travel, that is, the maximum separation of the interferometer and the retroreflector, has been reached. Upon completion of this procedure, the optics will be aligned. Rotate the target away from the return port and adjust the beam aperture control so that the large opening is selected. If the system has been properly aligned, the needle on the beam strength indicator should remain in the green zone over the entire range of travel. To make a distance measurement, press the distance key on the front of the display unit. With the toggle switch on the rear of the display unit, select English or metric units for the measurements. In English mode, the measurement will be displayed in inches, and in metric mode, the measurement will be displayed in millimeters. To change the selection, pull the toggle lever out, move the lever to the desired position, and release the lever so that it can lock into the new position. To select the desired resolution, use the numeral entry keys to enter the number of decimal places desired, then press the resolution key. In metric mode, the maximum available resolution is 5 decimal places, or 10 nanometers. In English mode, the maximum available resolution is 6 decimal places, or 1 microinch. Entering a negative resolution causes the normal data smoothing to be removed. Measurements may be made with sensors to automatically monitor environmental conditions, or environmental data may be manually entered. In this experiment, the data will be manually entered. Since the laser wavelength data is based on a refractive index for air at standard conditions, that is 68 degrees Fahrenheit or 20 degrees Celsius, 29.921 inches of mercury or 760 millimeters of mercury, and 50% relative humidity, differing environmental conditions should be compensated for by using the velocity of light or VOL option. In our